Okay, so we can get started. How is everybody doing on programming assignment 3? Who's attempted bin sub, binary subtraction? So binary subtraction all done. What about any to any? All good? And then what's the next one? Root finder? Good. And bin to float? Double to bin? All right, so we're at maximum at double to bin. Good. Definitely get started if you have not already. We're counting down, what, at this point, 8 days to when PA3 is collected. And every day, one of those days counts. You need the time to get stuck, get unstuck, to iterate, and debug. Good. So let's continue today. So where we left off before was we motivated why floating points is a good standard. It's got some trade-offs and kind of arbitrary points in it, but a lot of it, most of the floating point number system, it's a brilliant, it's a genius design, right? It has a lot of very useful properties that allow programmers to have this illusion of having access to a real number system, even though all of it is encoded in bits and bytes and binary. We talked about how to represent most normalized numbers, so most normal numbers in the floating point number system. It's essentially scientific notation, but done in binary. Where we're going to pick up now is denormalized numbers. Right? So actually, now that everybody's had a chance to at least absorb a little bit about the normalized side of things, is there anything that we should review or recap that we can make sure that we know about normalized numbers really well? Okay. So when we were introducing normalized numbers, somebody asked a good question, right? If it is claimed that in both scientific notation for decimal numbers, what we do is we make sure that there's exactly one significant digit to the left of the decimal. What do we do if the number is 0, right? For 0, there's really no natural place to put the decimal point. No matter where you put it, it is going to be 0. So we have a similar problem in the binary floating point number system, which is when we get to numbers that are very low in magnitude, around 0, we need a slightly different representation to be able to capture these numbers. So just as before, we already illustrated how the floating point number system, it invests most of its representable numbers close to around 0, right? And as you get to really large magnitudes, the spacing of the numbers that can be represented get spread wider and wider apart. And we see this exact same thing in the decimal scientific notation here, which is, with this at this range of magnitudes, the next number that you can represent with a given number of digits is already also a really large range, right? This is going to be a difference of 10 to the 21st in the increment. So the binary floating point number system has this exact same property. And then as we get very close to 0, an interesting thing that it does is it switches from what are called normalized numbers in these triangles, and it switches to a representation called denormalized numbers, or subnormal numbers in some places that you'll read about it. And for subnormal and denormalized numbers, they follow a slightly different set of rules, a slightly changed set of rules to get nice properties. So the set of rules that it changes to is the way that the exponent is encoded and also the mantissa. Both of them are encoded in a different way. So when we're talking about denormalized numbers, the exponent is going to be treated simply as 1 minus bias. Okay, how is this different from before? For normalized numbers, what were we used to? What was the rule for encoding the exponent capital E using the EXP field for normalized numbers? Yeah.
E was EXP minus bias.
So this is to contrast, right? I'm going to write this down, and then I'm going to erase it so you don't get confused. For normalized numbers, the rule was EXP minus bias. So now we're switching to the rule being 1 minus bias. And they're not the same, right? It's not just the same rule applied to a special case of EXP being 0, right? If you plug in EXP equals 0, 0 minus bias, that should be just negative bias. But here, the actual rule is one off from that, right? So it's not the same rule being applied for a special case. It's just a different rule, right? And exactly why that's useful, we'll get to in about 20 minutes, right? But just hang on while we explore what this does. And then the other change in rules is that the mantissa, the significant digits, are also encoded in a different way, right? The mantissa, the significant digits, are going to be encoded as there's an implied leading 0, followed by the binary point, followed by the significant digits of the fraction. And again, how is this different from normalized numbers? How is this different from what we're used to before? Yeah. Yeah, so I'm going to write this down, and I'm going to erase it just so that you don't get confused looking at the slides. Before, there was an implied leading 1 point something, followed by the frac field, right? So clearly, this is a different rule. Recap question. Why is it useful to just omit that 1 for normalized numbers? Yeah, for normalized numbers, we already knew, right? We know that there will always be a 1 there, so it's useless information to keep track of. So long as it's normalized, that 1 is always there, so we just throw away that 1 so we conserve a bit. So with that, let's explore these rules, right? So what I'm going to do now is going to be a fun little exercise where we explore the entirety of the number line. Let me pull up one piece of information that I need. Okay, so the format that I'm going to define now is going to be this format. And we'll use this to recap both normalized numbers and denormalized numbers. So the format here is going to be a 8-bit format where 1-bit sign. I'll have 4 bits invested in the EXP field. And the convention here is that it's called K. And the remaining 3 bits will be the frac field. And I'm going to now explore the entirety of the number line, right? So ranging from negative infinity all the way to positive infinity. And we'll write down a bunch of different numbers. right? So how would we encode positive infinity? So what would be this is the number we're trying to represent, right? Positive infinity. And in this format, how would we encode positive infinity? So step by step, right? How do we think about this? Any number that you want to write down, we have to represent it as -1 to the power of sign bit times the mantissa times 2 to the power e. Okay, so what's the sign of positive infinity? Well, let somebody else say what the sign, right? Is sign infinity, is infinity positive or negative? Yeah, positive. So what's the sign bit? 0, right? -1 to the power of 0 is going to be a positive number. And then the rule for encoding infinity is that what it does is it's encoded in the EXP field. So 1, 1, 1, 1 indicates that this is an infinite number, right? It's a special case where we reserve whenever the EXP field is the maximum possible number, that just encodes infinity. And the rest of the bits, same thing, encodes all the frac field bits will be filled in with 1, right? This is just a special representation for positive infinity. Yeah.
Does it matter what's in the frac fields for positive and negative infinity? Like, could it be like 0, 0, 1 in the frac field and it still be infinity?
It does. Oh, sorry. Sorry about that, right? So never mind. I just told you incorrect information. So positive infinity, EXP field will be the maximum possible number, and the frac field, no. The frac field is not filled in with all 1s, as I claim. Sorry about that. The frac field is filled in with all 0s. Right, good catch. So this is positive infinity. This is correct. So good, right? Positive infinity is useful in a lot of settings where, say, that you're trying to divide something by 0. 1 divided by 0, that goes to infinity, right? So the floating point number system will do its best to do something that is reasonable. Infinity just means a unrepresentably large number. Yeah.
If in the frac field it was something like 0, 1, 0, what would it be encoding?
So same good question. So that's still exploring kind of the other properties. So if you have 1, 1, 1, 1, 1 in the EXP field, and then in the frac field you have anything other than 0, this is a kind of error code that the floating point number system defines to indicate you've done an operation where there is no reasonable thing for it to keep track of, right? Say you perform an operation of 0 divided by 0, right? What should 0 divided by 0 be? There's no sensible answer to that. So it will give you a number that indicates not a number. Okay, so continuing with exploring our number line, right? So we just started at positive infinity. So what would be the largest possible number that you can encode? Right, so a large positive number that is pretty normal, is that going to be normalized or denormalized? Yeah, normalized. So largest pos number. What's the representation of that going to be? The sign bit's going to be 0. And the largest positive number that is not infinity, well, we can now use the EXP field as promised. So the largest positive number is going to be 1 less than the largest possible value in the EXP field. And for the frac field, it fills in with all 1s, 1, 1, 1. Okay, so that's the binary representation of what that number is. How do we interpret what the actual value is? In this number system that I just defined, 8 bits, k equals 4 EXP, 3 bits remaining for the frac field. How do we interpret what this value is? Yeah.
So it'd be
So let's slow down, right? So how do we decode what E is? Capital E in this setting, the rule is it's going to be exp minus bias. What's the exp field? So the exp here field in this case, what's that binary number? 1110. Yeah. 7. Is it 7? So exp is this. It's 14. And what is bias in this setting? So what's the rule for determining what the bias is based on K? Yeah, somebody just shouted out.
2 to the k minus 1 minus 1.
Right, so we continue to evaluate 14 minus, and what's that going to evaluate to? 2 to the k in this case is 4. So 4 minus 1, that's power third minus 1. So capital E is 7, right? Somebody said 7 just now. Maybe you were referring to, eventually, yes, the exponent, capital E, is 7 in this case. And how do we decode what the M mantissa is? We're in normalized numbers, so there's a leading 1 digit that's implied. And the frac field is 111. This is a base 2 number. And what is this as a decimal number? Yeah, somebody just shouted out. It's going to be what? So what's that going to be? 1.75 plus 0.125 is 1/8. So that will be 1.875. Right, so now we have all the information we need to decode what this number is. This is 1.875 positive because of the sign times 2 to the 7th, right? And we could evaluate what that is by hand if you wish, but that's what that number is going to be. Yeah, what's that number going to be? Yeah, we'll just leave it at that, right? So if somebody wants to type that into a calculator and just figure out what that is, it's easy to calculate, but I don't have it top of my head right now, right? So put a pin in that. Somebody tell me what that is. What we'll do next is, what's the next interesting number that we're interested in coming down? How do we represent just plain old 1? That's tricky too, right? How do you represent plain old 1? 1.0 something? Yeah.
You could represent it as like the exp field being, sorry, as E being 1 and the frac field being all zeros.
Okay, let me stay organized. We're getting a little bit multi-threaded here. So what is this value up here? 1.875 times 2 to the 7th? All right, I'm going to do this calculation. It's just 1.875 times 128. It's 240. Okay, so the largest possible number that this number system can represent is 240. How do you represent 241 in this number system? So you did a calculation and you got 241, and you're using this tiny floating point number system. What's the reasonable thing that it will do? Yeah. It will overflow into infinity. Right? So that's how, you know, despite the fact that 240 to us is a very approachable number, we have more days in the year than 240, but in this number system, the number of days in a year might as well be infinity, because that's the only way, that's the only sensible thing for it to keep track of. Okay, so we've done here, what we've done now is a bin to float conversion, right? This was an example of, I asked the question of, here is the largest possible number you can represent, and we decoded that into the the real number value that it encodes. What I'm going to do next is also important, which is I ask you a important number, 1.0, and what's the representation of that in this binary floating point system, right? And it's not super straightforward, right? So we have to decode this. What is 1.0 represented in how it should be encoded? Right? It's going to be -1 to the power 0. It's a positive number. Dot m. What is m going to be? It's 1.0 times 2 to the power of 0. Right? That is a kind of trivial decomposition of what 1 should be. So how do we encode this as a binary number? What's the sign bit? 0. What's the EXP field? What's the rule for decoding or encoding EXP? Right, so now it's a different set of unknowns. We know what the target E should be. That should be 0. Bias we had before was 7. Same number system. So in the EXP field, we want to encode 7. Right, so what should be in the EXP bits? How many bits are the EXP bits? K equals 4. Right, so what is 7 in 4 bits? 0, 1, 1, 1. Right, this is kind of weird, right? You should pay attention to this part, which is I have a very natural number. We know what 1 looks like as an integer. Right? As an integer, it's just going to be all zeros and 1. Super straightforward. But in a floating point number system, the very friendly, familiar-looking number 1.0 will have a very strange representation like this. Next part. What should the frac field be? Yeah. All zeros. Why all zeros? My mantissa was this.
There's no decimal places at the end, so there's no 0.5, no 0.25.
Good, right? The 1 that we do need to encode is implied already, so all we care is the frac field. The frac field, you can look, is just all zeros, so here is the binary floating point representation of 1.0. Right, that should be pretty interesting. 1.0 has a weird representation. What's the next interesting number? We've gotten 240. I've gotten 1. Between 1 and 0, there's still several interesting numbers, right? What is the smallest magnitude normalized number going to be? Right, and maybe somebody should just motivate that, right? Why is that an interesting number to study? Smallest positive norm number. What's the binary representation of that going to be? What's the sign bit? 0. And what's the EXP field for the smallest normal number, normalized number? Yeah.
Would it just be zeros and then a 1?
Zeros and a 1. Why not all zeros?
Because that's saved for the encoding of 0.
Close, right? I want you to think about it. So what all zeros in the EXP field is reserved for, yes, 0 and also denormalized numbers. So that's why for the smallest normalized number, the EXP field is not super straightforward. It's at least a 1, right? This will preserve that it's still a normalized number. And keep going, right? I'm looking at this number, and what's the smallest possible frac field that we can keep while it's still normalized? Yeah. All zeros. Okay, good. And what does this number encode? It's going to be -1 to the power of sine, that's 0. M, we'll figure out what that is, times 2 to the power e, and we'll figure out what that is. What's m? Well, the frac field's all 0, so that's just going to be 1.0. So now we're just curious of what the E is going to be. And what's the rule for E still in normalized number system? EXP field minus bias. So that's 1 minus the bias, which is 7, minus 6. Right? So this is plus 1 times 2 to the minus 6. So in other words, it's 1 in 64. Right? I don't know what the decimal representation of that is, but it's 1 in 64. Okay, so we keep going, right? What's the next interesting number underneath that? Yeah. Largest denormalized number. And what's going to be bigger, the largest denormalized number or the smallest normalized number in magnitude? How do we think about it? So it's been the same 4 people rotating around. Anybody over there want to chime in? You know, what's the point of denormalized numbers? Denormalized numbers are close into 0, right? So between these 2 numbers, which one do I expect to be larger in magnitude? Yeah.
Will it just be the largest denormalized?
So this number here is going to be a larger value. Largest denorm is going to be slightly less than that, right? So let's evaluate what that is going to be. What's the largest denormalized number? Its bit representation is going to be 0 in the sign bit, because we're still talking all positives. Now the frac field, sorry, the EXP field is allowed to be all zeros now, right? EXP field all zeros, that's for denormalized numbers and also 0 itself. And we're still trying to make this the biggest number as possible, right? So what's the frac field going to be? All ones. And what's the representation of this? Well, we've got an EXP, we've got a bin to float problem to do, right? I've written down an interesting binary representation. We're trying to figure out what's the real number value of this. And finally, arguably, this is finally new content for today, right? New content for today. We've encountered our decoding of our first denormalized number. So let's take a look, right? This largest denormalized number is still the same approach. But it's different rules for the mantissa and the exponent, right? So for denormalized numbers, the rule is now it's a leading 0 that is implied, followed by the frac field, right? The rule has changed. And what does this evaluate to? Well, it's 1/2 plus 1/4 plus 1/8. That is 0.875. Good. And the E, same thing. It's now a different rule, right? It is just 1 minus bias. 1 minus bias is minus 6. So this number is going to be 0.875 times 2 to the minus 6. Right? And you can take a look there. The difference here is very smooth, right? You can see that the difference between this number and this number is a very natural increment downward from the smallest normalized number. Any questions here? Right? This is a little bit tedious, but we're marching through. All right, so just now we've studied the smallest normalized number. We've studied the largest denorm, num. And we keep going closer to 0, right? What's the next interesting number? Yeah. Yeah, let's talk about the smallest possible number you can encode, the smallest positive number, smallest magnitude number you could possibly encode. And again, right, I'm just asking you this general question of what's the smallest positive number you could encode? Is it going to be normalized or going to be denormalized set of rules? Yeah.
It would be denormalized, but would it be just positive 0?
Well, is positive 0 positive? I would say no, right? Maybe if you're being very pedantic, I'll tell you, okay, the smallest positive number that is not 0. And what's this bit representation going to be? Well, it's going to be a denorm number, so all of that is implied. And to make it not plain old 0, well, the only thing we can do is just put a 1 there, right? That's a 1 there. And so the question is, what's this value? And by now, we're pretty good at this, right? I could jump to some conclusions pretty quickly that this is going to be 0.001. That's a binary number. The m is going to be that. This is just 1/8. And I already know what e is going to be. That's 1/6. So the number here is going to be 0.125 times 2 to the minus 6. Same thing. We can see a very nice progression, right? We can see a very nice progression of these numbers coming down from the normalized numbers there. The next one down is this number, 0.875, still at the same power of 2, and finally coming down to 0.125, same power of 2. Right, so here already, right, I kind of want you to start having this intuition, this feel of why the denormalized numbers are a good idea. Right, this transition from the normalized numbers down to the smallest possible value here, we stick to the same power of 2. Right? We stick to the same power of 2. This is why the rule for capital E had to change. And we have this very nice set of steps, 1.0, 0.875, 0.750, 0.50, 0.250, 0.125, finally all the way down to the smallest possible value. Does this make sense? Okay, what's next? Back to our number line. Finally, we hit 0. Right? And here, there's still something slightly interesting before we wrap up this little segment. Right? For 0, there's positive 0, which is as expected. And minus 0, with just a 1 in the sign bit. There. What else? Right? If I ask you, what about the other side of the number line? Do you want to go through that, or what's the one thing that has to change for all of this to just apply to the other side of the number line? Yeah. Yeah, right. We're not going to go spend another 2 pages redoing all of this, right? Everything on the other side of the number line is really all the same magnitudes, except we just add a -1 encoded in the sign bit, where the sign bit is now 1. Yeah, question?
In what situations would you represent -0 as opposed to +0 and vice versa?
Good question, right? What's the point of having a positive and -0? Right? If I ask you what is 1.0 divided by infinity, what should that be? Yeah. Well, it approaches 0, but from what side? The right side, right? So 1.0 divided by infinity, that approaches 0 from the positive side, so that approaches positive 0. What about this? Negative 1.0 divided by infinity. Yeah. This will be encoded as negative 0, approaching 0 from the left side. Right, and this has bearing in calculus and all that, right? This is important for these infinities and for these not-as numbers to encode in a sensible way that matches our intuition about real numbers. Yeah.
So when a number becomes too large for the EXP field, it just goes to infinity, it doesn't wrap around to the lowest exponent?
Would that be safe if we wrap around, right? So in integers, for integers, right, this discrete math object of the integers and the whole numbers, the binary number system allows you to wrap around, right? And the decision on why floating point numbers don't just wrap around is this is a lot closer to what we're used to, right? The whole design of the floating point number system is so that it creates this illusion of real numbers, even though the real number line, right? The real number line has an infinite amount of information, right? Any given precision of a real number, how many bits do you need to encode pi? Infinite number of bits, right? It's a transcendental number. But we create this illusion of the real number system using a finite number of bits, and it does that by having sensible rules on what infinity is going to be. And when you hit infinity, that indicates that that's just beyond what's the representable number. Along those lines, right, if you make a calculation here of what is the value of 1 over 128 in this number system, what will that evaluate to? So 128, is 128 representable? Yeah, 128 is representable, right? Everything up to 240 in this number system is representable, right? But if you perform a calculation of what is the value of 1 over 240, what happens? Think about it, right? Was 1 over 240 representable in this number system? It should be. How do you see that?
Because the smallest denormalized value was, I believe, 1 over 512, which is less than 1 over 240.
Where did you get 1 over 512?
I did the calculation somewhere.
Okay, so how do we quickly evaluate what I have here? What does that equate to? Yeah.
1 over 8 times 1 over 64.
So 1 over 8 times 1 over 64, that's 1 over 512. Yeah, so we're safe, right? I've got 240, 1 over 240 is going to be still larger in magnitude than 1 over 512. So it will do its best to represent that number, right? It might not represent precisely, but it will round it close to the nearest possible number it can use to represent 1 over 240. And why is this, okay, well, I'll do the next thing, right? Now why is that important, right? What is this property called in mathematics that when I take the inverse of 240, I get a sensible result? Any mathematicians in the room? Like, use all the jargon you know about the real number system to tell us what is this property called. Okay, so what is taking the inverse of 240, putting 1 over 240? What is that operation called? Reciprocal. What are other ways we call reciprocal? It's an exponent of -1, also good. Right? Let's come up with, let's enumerate all the ways we could call the same thing. Keep going. Yeah. Hooray! Finally, someone from that side of the room, and finally the answer I'm looking for. It is called the multiplicative inverse, right? And the real number system has a well-defined inverse for multiplication. It's called just taking 1 over the number. It's well-defined, and it's also called closed. So what does it mean for it to be closed under multiplicative inverse? Yeah.
If we're talking about rational numbers, if you multiply them, you'll get a rational number.
So if you have rational numbers, you take any two rational numbers, multiply together, you remain in the set of things called rational numbers, right? So for real numbers, you start with a real number, you take the multiplicative inverse, you still get a real number, right? It doesn't become some other thing in some other set, right? It doesn't become a cat or whatever, right? A real number, you take the multiplicative inverse, is still a real number. This property is called closure under multiplicative inverse. And the floating point number system does its darned best to maintain all this intuition, right? I take the multiplicative inverse of 240, and what I get is still a floating point number in this set. It does its best to represent 1 over 240. It does its best to represent the multiplicative inverse of 240, right? But it fails sometimes, right? How does it fail? What can I show now to show that it can also still fail to preserve multiplicative inverse closure?
The multiplicative inverse of the smallest positive number?
Yeah, right? So I can represent this number, right? It's right there. And I say 1 over this number, 1 divided by this number, 1 over 512. What does that become? What do we expect it to be?
512.
We hope it to be 512, but can it represent 512? No, right? And so what is the most sensible thing for it to do instead? It will just give you infinity. Yeah, right? And so this is a question on the quiz. It's probably the most indecipherable question so far, but that's what I'm getting at in the quiz, right? That the floating point number system does its very best to preserve these properties of real numbers. Okay, maybe we can, this is a good point to talk about some more of these properties, right? What other nice properties of the real number system are we accustomed to? What are some properties we know? Yeah.
Any number can be written as p over q, where q is not equal to 0, and they are in their most, oh wait, no, and they are in the most solution.
I don't know what that is. So multiplicative inverse is a kind of property. What other properties are there? Yeah.
I believe he's trying to say that each number can be represented as a rational number.
Each number can be represented as a rational number. Okay. Not quite super relevant to what we're talking about here. Yeah. Sorry?
The commutative
Commutative
property.
property. What is the commutative property?
It's the idea that you can switch the order in which, for example, for addition, you can switch the order and you'll get the same answer.
Okay, so good, right? I have two numbers, A plus B. Addition commutes. Commutes just means I can swap the operations on the left and right side, and it gives you the same thing, B plus A. Okay, isn't that obvious in mathematics? What's an example of some operation in mathematics that is not commutative? Yeah. Subtraction, right? Is subtraction commutative? So A minus B, B minus A, yeah, not commutative, right? So subtraction is not commutative. Good, right? So that's a concrete example. What other things are not commutative? Yeah.
I was going to say, isn't subtraction technically commutative if you take it as a plus negative b, and then negative b plus a?
Sure, right? So for subtraction, A, if you treat it as this, well, we're coming back to the actual operation. being addition, and yes, that is commutative. So I can leave that there. Yep, that's commutative. Yeah. Division is not commutative. So A divided by B not equal B divided by A. Good. Let's stay structured, right? Is multiplication commutative? AB equals BA. Is multiplication as a mathematical concept always commutative? Yeah. No, because of matrices, right? Why is matrix multiplication not commutative? Yeah.
It depends on the number of columns and rows. It has to be the same number of.
Yeah, right. So I can subset this. So say A is dimensions n times m, B is m times L. Well, if you take the commutation of that, B is dimensions m times L, A is n times m, the operation is not even guaranteed to be valid unless you have some very special property of L equals n in its size. Okay, so enough math here, right? So in general, is floating point addition commutative? Yes. How so? I'm turning this around to be a very open-ended session right now because I'm trying to think of the minimum example to show that it's not, but I'm drawing a blank. What if we added positive 0 and negative 0? That's still a safe operation, right? So we're studying this right now still. Yeah, I can't, I'll let you all try to think of some case, yeah.
Well, we said the maximum number we can represent was 240. So what if we added 238 and 239?
So we represent 238 plus 239. The commutation of that is going to be 239 plus 238. What's the sensible thing for this to evaluate to? Infinity. That also evaluates to infinity. Right, so both of them get to the most sensible thing it can do, which is just infinity. Yeah.
I think the issues start to arise when you have three and you involve like parentheses. So I'm also trying to think of an example, but like if you have, I think the example I saw on the quiz was like there's a really small number plus a really big number, but it's in parentheses, and then you subtract the big number, and
Good.
that's a different result if you change the parentheses around.
Okay, so I guess what I needed was the next property, right? Give me the next property that we're used to. Yeah. Associative property. What is the associative property? Yeah, right. So in mathematics, we're accustomed to this being true. The order of operations should not matter, right? I could add BC together first, or I could add AB together. The whole thing should evaluate to the same. Now, is addition in the floating point number system associative? Yeah. No, right? So how do we design a test case where this will sensibly fail?
Do like 240 plus any like denormalized number or any number at all really, and then minus like 239. Like it's not associated because this 241 is infinity minus 239 versus the actual answer should be zero. Should be not zero. Should be two.
Okay, good setup, right? Again, I should make an important note so that people reading the slides make sense. In the tiny float number system, right? Assuming we're carrying from the last couple pages, we're still in this 8-bit tiny float setting. The biggest number we can represent is 240. Anything beyond is infinity. What will this number system do to do the most sensible thing? So 240 plus 1, that goes to infinity, right? Infinity plus any finite negative number, what's a sensible thing for it to do? Infinity minus some number, yeah. It will evaluate to infinity, right? Because it just doesn't know. This infinity could be a billion or it could be 241. But it has no ability to tell the difference between a million and 241 to it. It's all infinity. And so infinity minus 239 is going to be still infinity. On the other hand, if the order of operations, if the association of the operations was done a different way, here I've got 240 plus, what's in the parentheses on the right? Minus 238. Can it represent both of these numbers? Yeah, no problem, right? These are all within the range of numbers it can represent. 240 is the largest positive number it can represent. Negative 238 is still smaller than the most negative possible number it can represent, which is negative 240. So no problem. It looks at this and says, yeah, that's easy. That's minus 2. Right? So herein is the interesting thing. These two numbers, just because we parenthesize differently, are not the same. Right? Addition is not associative in the floating point number system. Right? So these are things, this is very real, right? This actually, you as the programmer have to deal with this, is the scary thing. Right? This is not something that you can just tuck under the I don't know, the rug or whatever. When you're writing floating point code, you should expect that this type of stuff can happen. And so when you see infinities, when you see not numbers, it's your responsibility to know what is the real number that you're trying to calculate and what is the floating point number representation that the computer has on its hands. Yeah.
Should it be positive too, not negative too?
Oh, good call. Yeah. Okay, good. So all of this is good about numerical properties. Any questions up to this point? Well, we did a pretty thorough survey of what are the issues here. Anything that we kind of went through that I could explain better to help bring us up to the same point here? Yeah. Just to be clear, the bias setting of the bias is the same. So in all floating point number systems, yes, the definition of the bias is going to be this rule here, right? And for both denorm and for normalize, the definition of bias is the same. Yes? Good, okay, good question. Explore this some more. What about the distributive property? What is the distributive property? Yeah, just shout it out. Okay, so A times B plus C. Good. Can we design a test to show this show this failing? Okay, so let's target AB to be less than 240. I can make this fail. I have it, but maybe you should try. Yeah.
You could do in the parentheses 239 plus 1, and in A, anything that's not 1.
Okay, let's give that a try, right? So what you want to do, say that again?
In the parentheses 239 plus 1, and then you can put like 2 for A.
2 for A, right? So what will this try to do? So it will do, it can represent 2. It can represent 240. 2 times 240, what will that evaluate to? Infinity. On the other side, so 2 times 239 plus 2 times 1. So 2 times 239 may as well be infinity, plus 2, right? So in this case, both of them blow up. But I believe we can tune the numbers to illustrate the weirdness here, right? So let's try, yeah.
What if you make A 240 and then B positive 1?
Say that again?
A is 240, B is positive, and C is negative 1.
Okay, let's make another attempt to make this fail. Let's make A 240, and then
Like +1,
+1, -1. Okay, and then on the other side, so what will this evaluate to? 240 times 0, you'll get 0. And on the other side, 240 times +1 plus 240 times -1. So it will be 240 minus 240, which is 0. Okay, it was safe. So not quite. But we can still push it. We can try to push it to fail. Yeah, back there.
You let A equal 1/2, and then B is 240 and C is 1.
Say that louder. I couldn't hear you.
A equals 1/2, B is 240, and C is 1.
So A is 1/2. B is 240. C is
1.
good. And well, let's just erase all this. Okay, so what we'll do here, it will be 1/2 times 241. Can't represent that, so may as well be infinity. So half infinity, still infinity. On the right side, 1/2 times 240 plus 240 times 1. So 1/2 of 240, no problem. It knows that will be 120. Plus 1/2, no problem. It knows what that is. So it will evaluate to 120.5, or the best it can do to represent that number. Good, we broke it, right? So indeed, the floating point number system fails to preserve the distributive property sometimes too, right? And this is scary. Again, you as the programmer need to know when this is happening, right? The floating point number system, especially when you use a large system like the doubles, it will be safe in a lot of settings, right? For doubles, you have to try really hard to hit a number that it cannot represent, but it can happen, right? And in fact, I think based on what we see on Piazza, where people are trying to do the any-to-any problem, somehow using floating point numbers, and there's a question posed on Piazza that says, why is the number not incrementing anymore? Well, why is it not incrementing anymore? Well, you're starting to run into these things, right? You're taking some huge number. You're taking some huge number out in this range, close to what it considers to be infinity, and you're saying, hey, what is 1,000,000 plus 1? And to it, there is no such thing as 1,000,001, right? 1,000,000 and 1,000,001 may as well be the same number, so they map it to a million, for example, right? A million is probably not that dangerous, but out in the quadrillions, you will start having this problem. So suppose I have this number, right? Quadrillion, 1 quadrillion encoded in the double precision floating point number system. And you ask, what is a quadrillion plus 1? What's a sensible thing for it to do? A quadrillion 1, but it can't represent that at that number, right? So given a choice, right, I did 1 plus 1 quadrillion. In the real number system, it should be a quadrillion and 1. Right? To a quadrillionaire, what's the difference of $1? Right? Think of it that way. And so between two choices as you propose, right? One is to consider that to be infinity, and the other is to consider that just to be equal to quadrillion. What is the more sensible real number thing to do? It just reverts back to 1 quadrillion. Right? That's the sensible thing for it to do. When it truly becomes larger than the largest number it can encode, right? When does it actually go to infinity then? Well, only when you hit the biggest possible number it can encode and you go beyond that. Finally, does it hit infinity. So here, if the biggest number you can encode is 240, only when you try to encode 240 plus a little bit does it say that's infinity. Yeah. Okay. Good. So any continuing questions around this? Yeah. So could you encode 1 quadrillion and 1 in a double precision number system? That's a good exercise. Yeah, that's a good exercise. I think that's more interesting than what I have prepared. So let's explore this question, right? Let's explore how do we answer this, right? What's the best that a double precision float can do to represent 1 quadrillion, which is 10 to the 12. Okay, so how do we explore this question? What are proposals on what we can do here? Yeah.
First, it would be, like a positive number, so sets positive, and then you'd also have you'd want the largest 2 to the e as positive.
So let's do this, right? Let's first start with a stab at it, right? We need to have somewhere to begin asking this question, which is, well, what is about the representation? Roughly, what will a quadrillion look like in terms of bit string as a double precision floating point number? This is a great question, by the way. So how do we do this? This is a double to bin problem, and the double now is 1 quadrillion. So what's our mantra? Where do we begin? Is a quadrillion positive or negative? Yeah, okay. Quadrillion is you want to have a quadrillion in assets, not in debt. So good, right? So we know already sign bit's going to be 1. Oh, nope, never mind. That's not good. -1. And what's the next important piece we need to figure out? We should figure out what capital E is. And what is the binary representation, roughly, of this number? What's the trick here? What's 10 to the 12 close to? How many thousands is 10 to the 12? So it's 10 to the 3rd to the 4th. That makes sense? And what's the trick for 10 to the third? Yeah.
We said it was roughly 1024.
And what is 1024? Right, so already I have a pretty good guess, right? It might be off by a little bit, but I have a very good guess of capital E is probably 40. And how do we encode 40 as a EXP field? E equals EXP minus bias. And the unknown this time is I don't know what EXP is, but I know what E should be, and I know what bias is going to be. So E is the 40 we want to encode. And what is bias in this case? What is K, the number of EXP field bits for the double precision format? Well, we can refer back, right? I think I have a summary here. Summary is back all the way up here. So for double precision, K equals 11. 11 bits in the EXP field. So K is 11 minus 1. So 40 minus 2 to the 10 minus 1. So 40 hold up, I messed up something here. So sorry, what I copied down wrong was EXP is capital E plus bias, there, there, there. So it's going to be 40 plus 1023. So it will represent the EXP field as 1063 as a binary number. Okay, so our original inquiry, right?
Why
Yeah.
is it plus bias instead of minus bias?
So algebra, right? So this is the rule for E equals EXP minus bias. We know what E is. Yeah, so EXP is E plus bias there. Okay, and our original inquiry, right? What is the best that a double precision floating point number can do to represent 1 plus 1 quadrillion, right? Is to double precision floating point number, is there a difference between between quadrillion and 1? Well, we need more information here, right? So first of all, it has no proper problem representing 1 quadrillion. The next thing it has to do, it has to have a fight, right? It has to have a fight between what the highest precision it can encode in the frac field versus 1 at that point, right? I'm asking what I'm asking is when the EXP field is this big, when the E is at 2 to the 40, right? And to illustrate that, say out here, I'm at 2 to the 40th power. At that point, what's the gap between the closest two numbers it can represent? And is that gap bigger than 1, right? Can you fit, what's the smallest number you can fit in that range? So how do we figure that out? Right, so here what we need to do is the number that we can differentiate at this point is at capital E equals 40, what's the difference in value between 1.000 and 1.00 dot 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 001? 0, 0, 0. And how many bits are there in the frac field here? Yeah.
Do we say it's 52 bits?
Where do we can see that? go back to our reference. So at double precision, the number of bits in the frac field is all the bits that you didn't use in the sign and the EXP. So we're left with 52 bits in the frac field, right? So we have to ask when E is 40, the EXP is thereby encoded as 1063. What is the difference between these two values of M? Right, and to clarify that there are 52 bits here, 52 bits here, right? So already we can actually already eyeball this, right? What do we need to eyeball? Is 52 greater than 40? Yes, right? There are more bits of precision available than the power of 240 that's being used here. So in fact, even at the power of 2 to the 40, it's got 12 bits of precision that it can use to represent numbers less than 1. Right? It can take that range of numbers from 0 to 1, and it can chop that into 2 to the 12 different increments still. Right? So the answer to this question is, what's the best that a double precision float can use to represent 1 and a quadrillion versus a quadrillion? The answer is, it can represent the distinction between those two numbers very easily, actually. Right? In fact, it can distinguish between a quadrillion and 1/4000th versus 1 quadrillion. Does that make sense? Some blank stares here. Anything I can explain here to explain what's going on? Okay, so answer is, yeah, no problem. At 1 quadrillion, it can distinguish between it can distinguish at the power of 1 in 4,000. It has the resolution to do that. Okay. So what I usually talk about here to close out floating point number system is a discussion about what is arbitrary and what are designed aspects of a floating point number system. So I talk about the floating point number system is a great design, right? It's a marvelous encoding, a marvelous protocol. So still, there are some arbitrary choices in there, right? There's some arbitrary choices in there. So if you were to think about it, what are some parameters that could change in the floating point number system? If you were, in 1985 or 1985, part of the task force to design the floating point number systems, what would be things that you have to argue about? Yeah. How to represent non-rationals? Okay. Sort of. What else? Yeah.
How many bits you have to allocate?
How many bits to allocate? So what do you mean by that?
Because here we're talking about, like, for a double, you're allocating 64 bits. So you would have to, like, argue how many bits is required to satisfy some sort of number.
Yeah, so the question I'm asking you to think about is why they pick this? Why do they pick 8 bits in the EXP field, 11 bits for double precision? And the answer to that is it's just a good choice, right? It's the people who decided on it, I'm sure somebody said, no, we should have 9 bits. And some people said we should have 7 bits. and they went to go take a look at the numbers that people would be interested in calculating on, and they decided what's the balance between magnitude and precision that weighs the benefits of both, right? So this is a arbitrary choice, right? It would be a totally valid design to have all the same rules, but just to change around the choice of these allocations of how many bits you allocate to the two fields. What else is designed? Yeah.
Whether you care or not about negative numbers.
Whether you care or not about negative numbers. Well, would it make sense at all to ever design a floating point number system that could not handle negative numbers? No, not really, right? Again, right, the goal that they set out to do was to create something that is the ultimate goal, right? Something that is as close to real number algebra, real number mathematics as possible. And so we've been talking about multiplicative inverse. So they did so much to preserve multiplicative inverse. You'd be sure that they would do the easy thing to preserve additive inverse, which is just taking negative numbers, right? So negative numbers is certainly a first order thing that they've kept to preserve. Yeah. Is the order of the bits arbitrary? Right? Coming back to here, this picture. I've got to pack these pieces of information in this string. Why not move this over here or put the sign bit back there? Was this arbitrary? No. This is an excellent design. Why? Yeah.
It's for readability for the user, and it mimics how you would read it with scientific notation.
Both are fair points. Readability for users. Well, the users you're talking about here are just people taking 211, computer scientists reading bit streams, right? So readability for the user is not super important. And similarity to scientific notation, good, but not quite. There's a more subtle thing going on here.
What I was thinking is if you do an operation with negative, it's like subtraction where you have to negate all the bits, you'd want to realize that it's negative first. That way the pointer in the computer's memory doesn't have to move back and forth to negate all the bits.
I'll get to the point. The reason why the bits are ordered in that way, and in fact, another important point here, all of that is designed so that comparing two numbers is as if you're just comparing the bits for integers, right? You can test this out, you can work through this. You can compare any of these numbers by just comparing bit by bit, right? You start with the most significant bit. The most significant bit is the sign, right? If the two numbers are opposite sign, that's the most significant piece of information you need to know. And you can go through and compare MSB to LSB, and this is well ordered, right? So the floating point number system preserves a kind of order to ensure that comparison is easy. It progresses from MSB to LSB, and you're done. And that's a very important thing we talked about early on, right? On Tuesday, hey, we already talked about positive and negative numbers, right? We spent a couple days to explain sign magnitude, 1's complement, and 2's complement. How come, once we come to floating point numbers, we throw away 2's complement, which we argued was a brilliant design, and instead we mess around with this silly stuff involving the bias. And the reason for that is to make sure that comparing two numbers just progresses bit by bit, right? It makes the hardware easy to build. It's efficient that way, right? And then the kind of final subtle thing I wanted to talk about is, we didn't get to this. I'll use 20 seconds to say this, which is, why is bias designed to be this, right? This should jump out to you to be a magic thing, right? Why does the slide say that this is the rule? Why is this the rule? Well, the reason this rule is chosen to be this, we hinted at already, which is it's in order to preserve multiplicative inverse, right? We illustrated this here where we showed that the inverse, multiplicative inverse of 240 can be represented, and we make a choice of what cannot be represented. When you take a denormalized number and inverse this, that's fine. We might not be able to represent that, but any normalized number can always take the inverse, and that's why bias is chosen to be the rule that it is. All right, so we'll just close that out, and that's that.